Yeah, please let me know when I should start.
Yeah, I think we can start.
All right.
Welcome everyone. Welcome, Deborah Bajelovic. We are very happy to have Roman Geiko, and he previously studied at the Rutgers University under Greg Mo, and also worked at the UCLA. We are very happy to have him again at the CMSA. He will be speaking about what does 3D Chern-Simons theory, when does 3D Chern-Simons theory have time reversal symmetry? So let me remind the audience, please feel free to interact with Geiko or Roman and ask questions during the talk. Thanks. Please, Roman. Thank you.
Yeah, thank you very much. I appreciate your interest to our work, and yeah, so I intended this talk to be more like a blackboard. So yes, please feel free to interact, and especially so we have plenty of time, and I'll try to address these very concrete question at different layers. So yeah, let me start. So that's I'll be talking about one concrete work performed with Greg Moore, and the paper is already published, and his title is the title of my talk: When does three-dimensional Chern-Simons theory have time reversal symmetry? Right. So let me announce the plan. There'll be roughly 3 parts, not necessarily equal. I'll first remind you what's the classical data defined in Chern-Simons functional in the Abelian case, and then we'll spend most of the time in working on quantum Abelian Chern-Simons, and then I'll discuss quantum data for non-Abelian Chern-Simons, which is a modular tensor category of well, integral representations of highest weight of affine Lie group. Yeah, and the mathematical structures underlying this, the classical Abelian Chern-Simons will be integral lattices, and in the quantum case, this will be finite Abelian groups equipped with quadratic forms. All right. So we are interested in three-dimensional Chern-Simons with the torus gauge group, and we want to see this torus as a quotient of the n-dimensional real vector space by some rank n lattice equipped with a Gram matrix that we will call K matrix, and we assume it's non-degenerate. And naively, we want to write this Chern-Simons functional as a integral over 3 manifold with the Chern-Simons form. So this is yeah, so well, ADA is the Chern-Simons, usually called Chern-Simons form. And but in fact, this is not a good expression, because A is not a not always globally well-defined one form, and the way to go around it is to define it from 4 dimensions. So we do the standard trick. We see M3 as a boundary of some 4 manifold X4, and we extend our gauge theory into the bulk. And well, we know it is always possible. There is no abstraction, at least in the Abelian case. And so we choose some X4 bound in M3, and we choose some extension of the gauge theory into X4, and we define the Chern-Simons functional as an integral over X4. Well, we just basically using the fact that the omega Chern-Simons is F wedge F, right? And and similar formula for many fields.
Naive question.
Yeah.
So usually in condensed matter literature, we write this action of this K matrix with the coefficient of from as 1 over 4 pi. Well, here you have a 2 pi, which means you multiply by 2 a pi square. And
Right.
that probably means the cycle integration, one cycle of the A possibly pick up different quantization value, right? Probably pi.
Right. So this is
Pi.
my convention, right? So you probably want to see here 4 pi squared, or you might see 4 pi squared here, right?
Uh-huh.
Yeah, or so like in my notation, integral over f over s2 will be just well, will be an integer, and yeah, you might want to see 2 pi here, but yeah.
Okay. So
So in my notation, it's just an integer.
I suppose when the system is fermionic or the spin version of the Chern-Simons theory, the k will have odd integer.
Correct. Yeah, I'll go to that. Yeah.
But this normalization is, I think, differ by a pi squared for the first form when you write integration over 3 manifold, and when you go to 4 manifold, should you also multiply by a pi
So
squared?
normally f I think it is correct, because so normally f wedge f in the bosonic case is an integer in my normalization, and I want kii to be a even number, right? So if I integrate over a manifold without boundary, I'm getting an integer. Well, e to the 2 pi I times integer. So
Right,
so
naively.
so f wedge f over closed form manifold is integer. Kii is even, so everything checks out. We get in our just identity. Oh, you don't quite see, right?
Naively, I saw the coefficient in the second expression, integral over 4 manifold, probably the same as the one you have. So isn't that also 2 pi instead of just pi?
So okay, I'm sure in the second expression. So here it must be pi I.
Okay.
So you might be right that here it should be 2, or should not be 2. Okay. Let me just yeah.
Okay.
Okay, I'm not sure about this one. Sorry. The second one is definitely correct.
Okay.
Yeah, I tend to believe you're right.
Okay.
All right, so I wanted to say that so far I didn't mention that k is has integer coefficients, but if we want to this extension into the 4 manifold to be not depend, well, if we want our expression for the Chern-Simons functional to not depend on the extension, then the first k matrix must be integer valued, and also the diagonal elements must be even integers, right? So in other words, in the bosonic, but classical bosonic abelian Chern-Simons is defined by integral lattice with a even integral lattice. All right. So good. But I just want to notice that our gauge group is U1 to the n, which is a torus, and we can definitely get the same geometry by choosing different bases for the torus that we quotient by, right? But by the integral lattice we quotient by. And so we can just change the basis that is in our lattice that is given by transformation from GL and Z. And with this transformation, the K matrix will transform well, as a bilinear form should transform, as a symmetric bilinear form should transform. So in other words, well, we are not quite interested in lambda k as is. We are rather interested in this in the equivalence class with respect to these transformations, right? And what is a classical time reversal symmetry is, so if we change the orientation of space-time, our Chern-Simons form picks up minus sign, but then we can undo this transformation by just choosing different bases. So after all, yeah, it might happen with this integral magic. It might happen that we have time reversal symmetry at the classical level. So classical time reversal symmetry is just existence of solutions for the K matrix, just equivalence of K and minus K.
Question again. Sorry, just make sure. So
Yeah,
you consider only bosonic case right now? Is it?
Well, right now only bosonic. That's true, but
Right.
yeah, but right, yeah. I'll definitely talk about spin Chern-Simons. Yeah.
But probably that relate to the previous normalization because you do have a k along the diagonal is 2z, so that the extension to form manifold, that argument, that independent extension rely on that. When you have a spin version of this, I think the coefficient there probably can be 2 pi or something. Anyway.
So okay, I'll definitely get to this, but so far, in order to talk about again classical time reversal is just I have a, so if in the bosonic case I have just integral even matrix that is equivalent to minus itself, and in the spin case I'll just have a generic integral matrix, potentially odd, that is equivalent to minus itself. So yeah, I'm not so far I'm not missing much.
Okay.
Yeah, but I just want to well, you'll see later that
Please.
the problem is really complete only when you consider spin Chern-Simons. All right, so naively we can try to ask, like, can we describe all integral lattices that are anti-self equivalent? And well, so we basically solving matrix equations over Z. So these are a bunch of Diophantine equations. For rank n, the group of automorphisms of any one-dimensional lattice is just plus minus one. It has two elements, so it's just too small to accommodate time reversal. But well, also one can say that the signature of K, well, I just want to say that signature of K is minus signature of minus K. So time reversal changes the sign of the signature, and in one-dimensional lattices have signature 1, so they cannot even potentially be time reversal symmetric. All right, but in 2-dimension we have enough freedom. So in order to solve classical time reversal equations, we need to solve this type of equations. So we have 3 Diophantine equations, and I'm not sure if anybody solved them. Well, let's go over examples. So we have a known example of two decoupled U1 level K Chern-Simons, right? Of course, we have a transformation that just swaps the fields and swaps the sign. Well, very good, at least something. But also there is a famous example of this K matrix that is called fermion theory, and this is our favorite example. This is the simplest theory with a time reversal. well, maybe together with the toric code. So this is the semion-fermion, and we can just explicitly find the transformations that change the sign of this K matrix. And more generally, we can consider these diagonal type of K matrices with their, yes, they are, as you want to notice, that they are spin. So there is a odd number on the diagonal. And so these equations have solutions for the diagonal K matrices if and only if K solve this. This is called Pell's equation, or negative Pell equation. So, and it was allegedly pointed out by Edward Witten in 2016. And you can find more such solutions. Well, yeah, you can find more such solutions in this nice paper by Del Mastro and Gomez, the symmetries of the Chern-Simons in arithmetic. So they consider it 2x2 K matrices and found when they are classically time reversal and quantum. All right, so I'm not sure if I convinced you, but my point was that looking for classical time reversal is a very difficult problem, and it's hardly solvable. But in fact, well, it's not what we really need, because we want to quantize our theory, or we want to see our Chern-Simons, abelian Chern-Simons, as a effective field theory for abelian anyons. And we know that many classical functionals can lead to the same system of abelian anyons, or they can define the same invariance of manifolds.
Quick question?
Yes.
Sorry? So here you're not requiring the time reversal square to 1, are you?
I do not.
Okay.
Yeah, I just, yeah. And in fact, right, so in the semion-fermion, in this example, this squares to -1. Yeah, I just do not require that. And yeah, so here, I mean, here I end up with the part 1, and I go to quantum abelian Chern-Simons, because it is more important question, and it is actually more tractable. So one can take a classical data and quantize it, as was done by Belov and Moore in the paper Classification of Abelian Spirit Chern-Simons Theories. So they classify quantum data, and in their in their point of view, the quantum data is the data over a Hilbert space assigned to two manifold by this topological field theory. Yeah, and there is a very nice review by Spencer Stirling as well. Right, so the canonical quantization gives us a Hilbert space, and it turns out that this Hilbert space depends on much fewer data. It depends on a discriminant group, which is a finite abelian group. It's not a lattice. And this discriminant group is equipped with a non-degenerate quadratic form. And there is an extra piece of data. This is a remnant of the, well, the number that remembers the rank of the original lattice modulo 24. This is the signature, modulo 24. Right.
Sorry, a question
Yes.
I should ask earlier. So earlier you say in rank 2 matrix, you give us a non-example, right?
Yes.
I didn't get it, sorry.
Oh, it's not an example in the sense that it's very simple. It's not surprising that if I write a functional that looks like,
Oh, I see.
Yeah, A1 dA1
Yes.
minus A2 dA2, I mean, I just exchange the fields, and it's literally the same
But
looking theory.
it's still an example of a time reversal symmetry.
Oh yeah.
So which is the example?
This trivial example. Right.
Anyway, okay.
Yeah.
You see, example is not non-example.
It is, sorry, yeah, it is an example.
Thanks.
Yeah, so let me unpack this definition. So what is the discriminant group? To any classical lattice, to any integral lattice lambda equipped with the form K. So this is a bilinear symmetric form valued in the integers. And we can use it to, we can define dual using this form. So we can see it as a map from lambda to lambda star, right? Just taking the duals. And so this is their definition. So we first take our integral lattice and take its set of generators, and then we consider its rational span. And the dual lattice is a subset of this rational span such that pairing with the original lattice is integral. And the discriminant group will be just the lambda star defined this way by modulo lambda. And this is, well, this is the same as the co-kernel of K tilde. And if the original lattice is non-degenerate, then we'll have a finite abelian group. And as you might know, the finite abelian group is much more tractable object. So let's consider an example. So let's have a one-dimensional lattice and one-dimensional lattice with the K matrix 2. And this 2 is it means that's a bosonic theory. So lambda star here is just, can be seen as an integral span of the original generator E over 2. Okay. And indeed, if I pair the elements of the dual lattice with the original lattice, I'll get an integer. And the discriminant group is just the Z mod 2. And moreover, the original lattice K, so we had a bilinear form, and we can define a quadratic form that refines this this bilinear form. So it's going to look like, well, literally X. And when then you know, when we go to the discriminant group, we'll get X squared over 4. Roughly because the generator of the lambda star is E over 2. And we get in just a single semyon. All right. And of course, these two elements of the discriminant group, we know that these are integral representations of highest weight of U1 level 2. So this is a modular tensor category with two simple objects. All right. So the quantum data for bosonic abelian Chern-Simons is a finite abelian group equipped with the quadratic form. And it's interesting that since this quadratic form is non-degenerate, there are not many of them, not that many. And if we start with the simplest finite abelian group, Z mod 2, then there are exactly two non-degenerate quadratic forms. So the one is written here, and the other is just the opposite. So there is literally nothing else I can write down here if I want it to be degenerate, non-degenerate. So the other example is the discriminant group Z2 plus Z2 equipped with this form, and this is the Doric code. So this Q defines the topological spin. And well, for Z mod 5, we also have So we have x squared over 5. This is an example. Well, if I want to list all non-degenerate quadratic forms, then it's going to be 2x squared over 5, 3, and 4. X squared over 5. So unlike in integral lattices, I can literally write down all possible quadratic forms on finite abelian groups. And so we say that this discriminant group with a quadratic form is time reversal if there is an automorphism of D such that we can precompose our quadratic form and obtain its negative, its negation. So let's consider examples again. So in the first example, we have a semyon. Well, I mean, these examples are copied. So in the first example, we have a semyon, and we can just look at the topological spins. So we have two elements of the discriminant group, and their spins are 0 and 1/4. So there is no way it can be time reversal symmetric. All right. And in the second example, we have a toric code, and we have 3 elements, either 0 spin and the one with the 1/2, right? The fermion. Well, we don't need to do anything here. It's all automatically time reversal symmetric according to our definition. Very good. And well, less trivial example is Z mod 5. So the time reversal here, so this is the list of elements and their values of the quadratic form. Recall this is all mod 1. So the time reversal here is induced by multiplication by 2. So I just multiply by 2, 1 goes to 2, 2 goes to 4, and well, 3 goes to 1, 3 goes to 1, and 4 goes to 3. And indeed, all these arrows, they invert the value of the quadratic form. Great. These are examples of bosonic time reversal symmetric Chern-Simons. And now I want to comment on well, I want to mention spin Chern-Simons.
How do you choose quadratic form?
Oh yeah, so in the bosonic case, well, that's true. So in the bosonic case, if I just take the quadratic form that looks like okay, so I do the quantization, right? So first I start with the okay, let me start here. So we start with the classical integral lattice lambda k, and then we can define k is bilinear. And then we define a quadratic form, which is always possible. This is a good definition for a quadratic form because k is even, right? And then, well, we go to D, lambda star mod lambda, and, well, so, and we just extend k, and we extend q by linearity. Well, extend k by linearity, and just extend q by, so I'm just saying that this k and this q, they induce a symmetric form on D and a quadratic form on D. So for example, here, I had a bilinear form, and the corresponding quadratic form is just 1. It evaluates as 1 on the generator. And now I know that the element of D is just E over 2. So now I'm just evaluating Q on E over 2. But this is quadratic, so I know it's going to be 1 over 4.
So let's give one example, like the Z2, Z2, 2Z2, Z2 O plus case. So in that case, you can have a possibly include both the Z2 torical, which you are written here, and also Z2 double semion, which possibly is a plus x squared over 4 plus y squared over 4, and possibly other cases, is it? So the generic form or the quadratic form has several possibilities, including the one you write down and like the second example, is it? Do you follow my point here? So if I look into
okay, so let's not mention semion fermion so far, but you're saying double semion, right?
The second example, like example, you have the green 1, green 2, right? So the green 2, you have a 2Z2, right?
Yes.
And then you have a quadratic form Q depends on X and Y. And both X and Y are Z2 value, is it?
Yes.
And then I say the generic quadratic form possibly also include x squared over 4 and y squared over 4.
Oh, yes, yes. But it's different class, right? That's right. That's right.
Class, yeah. So I'm just trying to add the generic form there. So certainly the one include x squared over 4 plus y squared over 4 will be double same.
And it's right. So I think I agree with that.
How do I know the generic form? I guess that's the question I was asking, because you are writing a.
Oh, you asking a generic form of like abstract finite form on a finite abelian group, or you asking how do we get it from the lattice?
Just in principle, I think, because you give some example, but maybe I missed the how do you determine what are the form and what.
Oh no, I'm saying that, you know, if you start with a K matrix, you know everything.
Okay.
Yeah, and this is how. So this is our integral. So in this example, this is an integral even lattice, right?
Right.
So it just says that, you know.
So the Q quadratic.
So it's 2mn, right? And I can simply define a quadratic form that refines this bilinear form. You know, just m squared does the job, right?
So Q is directly given by K.
Yeah. In the bosonic case, there is no issue. But just in one slide, I will be talking about spin case, and this is more tricky. This is going to be more tricky.
But the third data, you also mentioned the signature Ma24, but the signature of the K matrix.
Yes.
But which is also given by K.
Yeah, it is also given by K, right?
So classically, we study K matrix, but quantum mechanically, even just given K, do I determine all the 3 data, 1, 2, 3 that you list?
Yes, absolutely. Yes. Yeah. So so the idea is just, right, thank you for the question. So the idea is just to, you know, make it abstract and, you know, just forget about the lattice and, you know.
Yeah, I know.
We just basically trying to, you know, list you know, objects that classify quantum data, and we can actually prove that any such triple comes from a lattice.
Right. So then, if I suppose I forget K, then you say you have a way still list the 1, 2, 3 data. So
no. So if I have K, I have a procedure how I define this 1, 2, 3. In the other direction. So and now I don't want. So I do not even want to think of K. I just you know, I just, you know, work directly with this data.
Yes, but then I ask, how do you write down Q? If you
from K or
no, because you say you don't need.
I just want to find all D's and Q's and sigmas. And if so maybe.
So I guess my question was, what's the coefficient of the quadratic form of Q?
Oh, it's fixed. It's fixed by the non-degeneracy condition. Well, and there are lots of isomorphisms between them, right?
And non-degeneracy in terms of K matrix will be determined K is not
Oh, no,
zero.
no, even in terms of I can say, let's write down some random finite group Z mod 3 and non-degenerate quadratic form. So first of all, we can say that a bilinear form on this group can be non-degenerate, and it must look like xy over 3 or 2xy over 3. There is nothing else I can write down. And in these cases, I can just define. So there are two.
How about x squared over 3?
No, this is a bilinear form, and this is a bilinear form, and then I can define a quadratic form that refines this. So there are two bilinear forms, xy over 3 and 2xy over 3, and the corresponding quadratic forms will be 2x squared over 3 and x squared over 3. Well, because I can divide by 2, and multiply by 2 mod 3. Okay. So first of all, do you believe me that this is a non-degenerate? So these are only two non-degenerate bilinear forms. So I'm checking that, for example, 3x and 3y must be 0 for any x and y.
Mm-hmm.
And also, I'm checking that, it's non-degenerate. It maps me D to, I can define a map from D to D star, and this is going to be a isomorphism. Yes. I'm just trying to say that it defines a non-degenerate parent, but it just means that this coefficient here is I can write any coefficient here, and this theta must be invertible element.
Mm-hmm.
So there is nothing else I can write down. And there are just two invertible elements modular 3 is 1 and 2. And then, so once we settled on the bilinear form, I'm solving this equation for the quadratic form. So I'm finding a refinement for this bilinear form. So that solves this equation, satisfies this condition.
Mm-hmm.
And again, nothing else I can write down. This is like 2, and this is there are just
Mm. So the thing that I don't know what I can.
So normally I want to define q of x as a b of x over 2, and here division by 2 is the same as multiplication by 2 modulo 3. So that's why I'm getting 2x squared over 3. Maybe I'm just too cluttering it here. Maybe find another place. Yeah. So
yeah, I think I get it.
Mm-hmm. So yeah, and again, starting with the lattice, as long as it's even, I'm simply defining a quadratic form on the lattice. Then I pass to this discriminant group, and it's very explicit. And I just substitute, my these generators, so to say, and I am obtaining corresponding quadratic form. So this is going to be xy over 2 on D, and the quadratic form will be x squared over 4 on D. Right? Because the generator of D is sort of E over 2. Okay. Yeah, maybe, to be more uniform, I want to write xy here. Does it, is it clear? Or?
Yes, it helps.
Right. And So yeah, instead of playing with the lattices, we go to quantum. We go to finite forms.
So
Yeah.
invite me when it says Z3, do you have a time reversal?
Oh no,
No. And Z4 you have?
no, we don't actually.
No, people know.
Yeah. So for Z3, again, we can just check, by looking at the values of the quadratic form. They must be symmetric with respect to inversion. Yeah, Z3 is not, and Z4 also never symmetric. But I still want to say more about this semyon theory. I put this asterisk here because it's actually, yeah, this system of anyons can be made time reversal symmetric if we include the spin structures. And now I'm assuming that all my 3 manifolds and extending 4 manifolds are spin. And
Actually, sorry,
yes,
for Z3, you get the quadratic form Q is x squared over 3. And you have a 3 input 0, 1.
yes, 0, 1, 2, 0, 1 over 3, and 4, so it's 1 over 3.
3, it's 3. And is that okay or not?
No, I mean it's not, because if I had time reversal, then I would have different 2 prime and 1 prime, and I want them to have spins 2/3. Sorry. Yeah. I want some, I just want to relabel my elements such that, their values of the quadratic form are inverted, nothing more.
Okay. Okay, thanks.
Yeah, so here, yeah. So this Q, I guess I'm forgetting to say that Q is a map from D to Q mod Z, right? Yeah, I guess I should say that.
Okay, thanks.
Yeah, so everything is mod 1. So these are all, again, literally topological spins. Or conformal dimensions. Yeah, so, and 4/5 is -1 over 5, mod 1. All right. So in the spin case, the integral f wedge f over any four manifold without boundaries is a even number, and that allows me to have kii to be odd integer. So now we really consider all lattices, all integral lattices with the integral symmetric bilinear forms on them that can have any integers on the diagonal and everywhere.
So,
and yes.
That's a
Yeah. No, it's great.
In the usual, there's a Bolzani modular tensor category language, even for Bolzani system, which include the Abelian Chern-Simons theory for Bolzani case for the U1, this gauge group or power of the U1. So the data there is the modular S and modular T and central charge. And in your version of description of data, then you will use the quadratic form Q, possibly to encode the braiding data, which is the include the T matrix and possible also S matrix.
Yeah,
right?
so Q
Well,
Q is quite literally connected to the
spin statistics.
Yeah, to the to the T matrix. Well, I mean, Tx is literally 2 pi Q over X. But it's more tricky with the B, slightly more tricky. But the whole idea is that up to gauge equivalence, up to unitary transformations on F and R matrices, these pointed MTCs are fully captured by DQ up to gauge equivalence. Okay.
So what label the modular S data also from the quadratic Q or bilinear form or the modular?
So I want to say that S xy is gonna be just e to the 2 pi I is xy, Is it
Probably.
so there was that was more tricky.
That's correct.
Yeah. And should there be two exactly? I'm not sure about two even.
Two.
Okay, good. Thank you, Max. Okay. Yeah, right. So
and the signature mod24 is the same as chiral center charge mod24.
right. And this, in different context, it can be like it might mean different things. So some people want to know the central charge like as an integer, and right. So in Chern-Simons, because we want to know the framing anomaly, we still want to know the central charge, at least mod 24. There is no, well, we can't capture more as a more fine like an integer, but we definitely want to know it mod 24. So for example, if I have a K matrix E8, which is unimodular and which has no anyons, but its signature is 8. So right. So it's still a non-trivial 3D TQFT in our approach. But I don't want to talk too much about this central chart because it's kind of easy to adjust it, and
Yeah,
it's
no problem.
it's not a big obstacle.
Thanks. I think
no
it's clear, more clear.
Yeah.
Thanks.
All right. So yeah, the classical data is now any integral and odd lattice, and the quantum data now is in the spin case is more slightly more elaborate. So we have the same finite abelian group, and we have a bilinear form on it, and we have a quadratic refinement for this bilinear form instead of a quadratic form. So usually when we say a quadratic form, it must satisfy this equation, right? So being a quadratic, so in particular, Q of 0 is 0. But here we relax both of these conditions for quadratic refinements. So first of all, Q of 0 might be non-zero, and yeah, I use hat to distinguish quadratic refinements from quadratic forms. So Q of 0 might not be 0, and the new condition is this. And this is the only one condition that we need to satisfy.
So, sorry, Roman, quick question.
Yeah.
So your D, is it going to include for any on A, is it going to include A times the neutral times the trivial fermion, or it only is kind of half of that?
It is half. So this data it includes only the R sector. So an S sector is simple. I mean, I just
No. I'm not talking about vortices. I'm not talking about pi fluxes. I'm talking about, let's say I have a semi-fermion theory.
Yeah.
So then, you can say, okay, there is a particle 1, there is a particle S, there is a particle F, and there is a particle SF. So I could think of it in terms of those 4 particles, or I could just think about it in terms of particles 1s, because, the fermion is transparent. So which approach do you want to take?
I want to take so this, I do not see the fermion. Yeah.
Sorry, you do not, you only have two particles in that case.
Exactly.
One S.
Exactly.
Okay, got it. Thank you.
Yeah. So more precisely, this data in the green frame, this will be F and Fs. and the guys living in the R sector in my language. And well, 1 and S, I'm not even considering 1S, I'm considering FFS. Okay, and now I want to talk about how do we get this quadratic refinement from a lattice. So thanks to Juven's question, we now have an idea that so if we have a even lattice, then we just can divide by 2, and it defines as a fine quadratic form.
Sorry,
But,
Raman, just maybe to go back. I mean,
yes.
F and Fs is not closed on diffusion. So that's a feature that you want?
Yes, it is actually, yes.
I mean, isn't it just simpler than to work with something that's closed under diffusion?
Well, it's all coming together, and it's completely equivalent to what you have in mind. I can assure you that. But yeah.
Okay.
And later, when I'll write down the full spin MTC, that does not really define a spin MTC, because indeed, if I have 2 sectors, and the R sector indeed is not closed. But yeah, I'm just trying to define the so an S sector is, well, it's not different from a bosonic theory. Right. So and if I know the R sector, I know the NS sector as well. So
why do you call them R and NS in this case?
Is it well, because this is like something associated to a circle with periodic boundary conditions. So this is a
I is for periodic.
Oh, you mean the spin structure? You mean the spin structure here?
Yeah, NS is for the anti-periodic.
Yes. So this is the usual boundary condition. These are periodic boundary conditions. Like these are right, and like bounding and non-bounding circle, and yeah. So
I thought that has to do with whether you have a pi flux or not, right? Whether I mean, that's like another matter, because you also have, like in any, well, if it's really a 2 plus 1D fermionic theory, then you can also think about modular extension, and then that introduces vortices, and that's like your Ramon sector. I don't think this is about this particular.
Yeah. So what I mean is just a simple thing. Like so if we have an MTC, we associate we associate something to circle with the even spin structure and with odd spin structure, right? And this is what I call an S and R sectors. Yeah, just pardon my terminology. I mean,
maybe this is like in the time direction. Those are the okay.
No. These are like spatial circles. Like if I have a 3D, well, I have 3, 2, 1 TQFT, so it associates something to 3 manifold and Hilbert space to 2 manifold, and this category to 1 manifold. And that's why we have a monoidal structure, that we have a multiplication, right? Because of these Bordisms. And yeah, I mean, I'm a bit confused because you are confused.
That's okay. That's yeah. Feel free to go ahead.
Yeah, after all, it should be.
I think that is you are just trying to separate the Hilbert space to bosonic Hilbert space and fermionic Hilbert space, right?
I guess yes, it is right. Yes. Well, that's yeah. I believe that this is a correct statement that I have here. I have F and Fs. It's not even. Oh well. Wait a sec.
S is what? Sorry, semion. What's S?
Yeah, S is Semyon, F fermion. All right. So okay. The truth is the truth is that after all they all are together. So after all, I'll define a spin, a super MTC, and all these guys will be there, the fermion and the others. Yeah, sorry. All right. Yeah, I guess I was wrong, right? So I'm still bothered. So I have one semyon, fermion, and semyon fermion. And if we are careful, then if I have the semyon fermion K matrix, then what we'll get from this machinery is two Z2 with the two spins, and the spins will be so this will be SF particle and an S particle, right? It's going one quarter, yes. Yes. All right. So let me tell you, let me tell you how to obtain this quadratic refinement, right? So the quadratic, we can just have a quadratic form, and there is no canonical way to obtain a quadratic refinement, but there is a standard way to obtain the refinement. So we pick a characteristic vector from the dual lattice, and it satisfies this condition for all elements of the original lattice. So K mu mu should be the same parity as pairing with the W, and then we will have a good quadratic refinement. And so this is a constant coefficient, but it's here for the convenience. And interestingly enough, this is an integer number. So K of I can divide by 8 and still obtain an integer number. And yeah, so this is the example of the semyon fermion. It's a rank 2 lattice, and the characteristic vector here is can be taken as the second basis vector. And if I'm careful enough, this is what I am obtaining as a quadratic refinement. So I'm having two elements with the spins why I'm having 8 here. Sorry, it's not 8. It's 1/2. Sorry, here it's 8, and yeah, so I'm having wait a sec, I think I'm here. No, it's -1/8, right? So I'm so confused with these spins. So yeah, it's going to be -1/8 and well, +1/8. So this is what I am obtaining after quantization. And this is a transparently time reversal symmetric. Well, first of all, because the values are opposite, but also I should mention that now I'm not having a quadratic function, but a quadratic refinement. and I'm allowed to not only apply some automorphism, but also I can shift by some element of D. So here Z2 doesn't have any automorphism, but there is I can just shift by one. I can just add a vector. So this is like a fine linear transformations. All right. So upon quantization, I'm obtaining 4 pieces of data and find the Abelian group, symmetric form, quadratic refinement, and a signature mode 24. As I said, it will emit the signature. And in fact, if I have a quadratic refinement, I can restore the symmetric form. So we'll be interested in fact, we'll be interested only in the pairs of quadratic forms in the bosonic case, or quadratic refinements in the spin case. And as I mentioned, so here are examples. So as I mentioned, in over Z2, there are only 2 quadratic forms, and there are exactly 2 quadratic refinements as well. Sorry. So there are more than, okay, yes. So in the spin case, as we mentioned, this is the quadratic refinement corresponding to the semyon fermion. And we can have another one. I guess it's going to be something like anti-semyon fermion. And these are 2 different time reversal symmetric theories that we can have on 2 elements.
Sorry. Anti-Semyon fermion is the same as semyon fermion.
Right. So let me. So this is something. Right. So it's going to be 3/8, and right. So after all, let me take it back. So after I. So yes, super MTCs defined by these quadratic refinements will be the same. There's just one of them. Yes. Right. Yeah. So I don't think it's a good idea. Well, at least for me, to identify this quadratic, so this discriminant group and concrete anyons. So it's definitely here in the bosonic case, but in the fermion case, it's slightly more confusing. But I'm assuring you that after all, the results will be correct. So this is so I want to work with these quadratic refinements instead of like quadratic forms plus a fermion or something. Right. Yeah, but I think at this point, we should not identify these elements of D, in the spin case, elements of D and some concrete anyons. So in Z, and there are 2 isomorphism classes of quadratic forms over Z5, and I also can add this 1/2. So, and they are both time reversal symmetric. Yeah. So let me now tell you.
May I ask something?
Yes.
So, what's the meaning of this Q hat 0? Just make sure you especially said it can be non-zero.
Yes. Well, I mean, I'm imagining this is like a R vacuum, the spin of the R vacuum.
And if it's non-zero, what's the available value for this? It can be 1/2, 1/8, or
it should be a fraction of 8. Like it should be a multiple of 1/8 for sure.
Okay.
Yeah.
And so what's this number k/8? This k mean here for this multiple, plus for this k in Z8. Just make sure. What's this Q hat 0? The allow value in whatever fraction.
Yeah. So Yeah, so this is right. So
in physics term and in math term, just make sure I get it.
well, so in math term, this is a kind of famous invariant. So for any lattice and so and here it just shifts the topological spins such that we obtain in the right relation between it just fixes the Gauss sum, right? So I just add in some constant term and it just fixes the Gauss sum to what we need. Because we expect that we can calculate the signature of a K matrix, right? And when we quantize, we still have these Gauss sums, right? And it must be a multiple, it must be a eighth root of unity. And this coefficient fixes me the ambiguity. First of all, it fixes the ambiguity and gives the right relation, but it's not the only choice. So here it's again it's kind of tricky because yeah, because there are more relations. So quadratic, we all know what like two equivalent quadratic forms are, what it means for quadratic forms to be equivalent. It just means that we can precompose with some automorphism. But now we are allowing a shift. And it's just, in physics terms, it just signifies that the R sector is a modulo over an S sector. I can always, multiply elements of the R sector with the elements of an S sector. So this shift symmetry means that, the R sector is not a category by its own. It's not closed. It's a modulo over an S sector. Yeah, that's how I see it, at least. I think in common terms, but
okay.
Yeah.
But what's this particular modulo A value mean? Is the central charge of the?
Oh no! This is I mean I can see it as the spin of the vacuum of the air vacuum.
But why the vacuum carry other than
Yeah, it's
fermionic spin?
No, it can be anything, right? Like,
But okay.
so even in the
You mean on sphere or on torus?
on a circle.
On sphere, because it's 2 plus 1 d TQFT.
No, it's 3 to 1. It's 3 to 1. Right. It assigns me an empty C to S1 in the bosonic case, right? And in the fermionic case, I have two spin structures on S1.
But what's this S1 in terms of a 2 plus 1D material that produce this TQFT means? What's this S1?
Oh, this is I guess this is the well, so yeah, it's one of the special circles. So if you look at the conformal boundary, then this will be the S1 of the conformal boundary. Well, the conformal boundary is 1 plus 1 dimension, and this S1 will be the S1 of the corresponding CFT.
So you'll put these materials, let's say if it's a condensed matter system, you put these materials on some 2D space with an S1 circle boundary. And then you say there's some spin or angular momentum of this S1 circle. And that can be read from this 1/8 times some multiple integer mod 8. And that integer is related to this the boundary gapless modes.
No. It's still a conformal dimension. It's still a conformal dimension of the vacuum.
Yeah, just in case.
So, well, I mean, okay, I think it's easier to understand in terms of a CFT. So,
in terms
well,
of more
in a
realization.
CFT, we have a like primary fields. Well, we have a vacuum modules. We have like the standard vacuum module is 0, has a conformal dimension 1. But on the CFT with this spin structure with the and so we have an S and R sectors in the CFT, and this R sector, the vacuum of the R sector, need not have a 0 conformal dimension. I don't remember. Yeah, I don't remember the exact example from top of my head, but
yeah, I'm trying to convert to more like a physical realization language, just in case you know, but you can just
yeah,
convert.
no, that's the best I could come up with, but because and I absolutely agree that this is slightly not standard, but this is what we obtain from again canonical quantization of Chern-Simons fields. And this is true, but yeah, spin case is a bit confusing. But okay, so I don't know. I still want to go over a couple of slides, and so the result, the final result will be so the symmetric pointed super MTCs are time reversal symmetric, and they have this form. So
By the way, you can take your time. It's fine.
say again.
You can take your time. It's not you can.
Oh no! I'm just so I just want to demonstrate that after all, everything will be formulated in the usual terms. So in super MTCs we do have an explicit fermion that is a non-trivial element of SVEC, right? So SVEC has 1 and F. So DQ, we have a full control of them. So these are bosonic anyons. Well, I'm going to tell you what bosonic time reversal symmetric abelian anyons look like, but if we feel like we have a control over them, then the spin MTCs look like we take a bosonic fermion plus we take this semyon here. These are literally semyon, and tensor them with a fermion, and this is going to be the right one. And there is no any quadratic refinements, as you can see. So after all, the answer is not no quadratic refinements, no this the thing we're trying to discuss there actually the final answer, and this is I guess this is what you were asking about, because MTC definitely contains the data of anyons, and at the end there is no nothing surprising here. So I'm literally obtaining a one semyon, fermion, and SF. Okay. So, and again, after reconverting this stuff, there is no Q hat, and this doesn't play a role.
Sorry, what do you try to say? Are you trying to say the Fermioni version of the TQFT, if it's time reversal invariant, then there's a counterpart for the bosonic invariance, a bosonic TQFT that's also time reversal invariant, and they have a 1-to-1 correspondence, so they have some map between them.
Yeah, so roughly yes. So well, because pointed MTCs are very simple. They all look like CDQ times SVEC. So SVEC always this fermion always splits from abelian anyons, right? So in general, if I have a super MTC for spin theory, a fermion can be non-trivially, can have non-trivial braiding with everything, and so it can have non-trivial braiding with stuff, and it doesn't like split like as a tensor product. But here, in the case of abelian anyons, you can always factor out the fermion. That's just a feature of abelian anyons. Yeah, Tigran. Sorry, I mean I want to announce the result, or I don't know.
Can take your time.
All right, so let me just overview what I want to say, and then we can see. Right. So we just use the, first we use the fundamental theorem for finite abelian groups. They all split into these CELO subgroups. So here are Z2s, Z4s, Z8s. Here are Z3, Z9, Z27, Z5, Z25. So they all split. They do not interact with each other. So if we want to look for time reversal symmetric stuff, we can consider these all prime subgroups separately. And moreover, we should separate Z2, sorry, 2 prime subgroup with all others. So odd cases are simple and really tractable. But yeah, we know the full answer anyway. So right, so if I have any specific prime P, so any P prime a subgroup further decomposes into homogeneous paths. So I have some number of copies of ZP, then ZP squared, and so on. And these decompositions are orthogonal. So if I have D decomposed into prime components, then the finite, then the bilinear form also decomposes, and bilinear form also decomposes into the homogeneous components on Z3, Z or ZP, ZP squared, and so on. And the wall theorem, it tells us what are the generators of this decomposition, the simple non-divisible forms. And so there are only 2 types of generators if P is an odd number. And so it's, they look like that. So we just take any theta, which is a quadratic non-residue. So there are 2 types. And for 2 prime groups, there are much more. And so, okay, good. I want to stress that this decomposition is not unique. So we know the generators, but there are many relations among them. So I can decompose the same group into up to isomorphism into there are still like remaining. So I use various isomorphisms to decompose my form into a sum, but there are still more isomorphisms that allow me to represent this form in a non-unique, so they're in a different way. So for P odd, there is just one relations on the generators. So there are 2 types. I call them X and Y, and X plus X is isomorphic to Y plus Y. And this allows us to classify time reverse symmetric forms. So using this relation, I can either, so I want to get rid of this extra like gauge equivalence, and I want to bring them to the standard form, so I can compare if 2 forms have the same normal form, then they are definitely isomorphic. So I'm getting rid of as much Y's as I can, and I'm bringing the forms to this standard form. I'm just left with either all x's or just one y, thanks to the relation. And now, looking at this normal form, I analyze time reversal symmetry. So first, if P is equivalent to 1 mod 4, then -1 is a quadratic residue mod P to the R. In other words, there is a number A that squares to -1 modulo P to the R. And I use this number as an automorphism, so it's definitely invertible. And I just precompose my form with this number. And since it squares to -1, it gives me the isomorphism of the form xy and minus xy. And it works for both types of forms, of course. So if P is 1 mod 4, then literally any form is time reversal symmetric. This is nice. And if P is 3 mod 4, it's more tricky. So the basic form X is not time reversal symmetric itself, because minus xy to the P to the R. So -1 is not a residue, so it's different class. So and time reversal actually exchanges these two classes. But then I can take a sum, and time reversal will just swap them. All right. And just summarizing, we can fully classify time reversal symmetric forms on ZP with the P odd. So we had this decomposition D plus D2 plus D other P's, and the second part is completely classified. So all we need to care about is D2. And again, there are lots of generators and lots of relations actually. And what is really makes them difficult is that there are relations that go across homogeneous components. So, but anyway, so there is a nice invariant that allows us to, first to bring them to the normal form, and it just abstractly classifies the forms. And this is called Kawauchi-Kojima invariant. And in a simple terms, this is just a higher Gauss sum. So I'm just taking all possible Gauss sums with my form, and so they might get 0, and this is fine. This is still very important information. And we just it's either 8th root of unity or it's 0. And we just say that this Kawauchi-Kojima invariant, it takes values in 0, 1, 8, and infinity. So, sorry, 7, infinity. So these 8 numbers, they correspond to the 8th root of unity that we can get. Or if the Gauss sum vanishes, then we say that the invariant is infinity. And we can compute this invariance for all generators, and we use this and we use these values to classify the forms. In fact, only 3 values unknown are independent. So right, and if 2 forms have the same higher Gauss sums, then they are isomorphic. And we can check that time reversal simply reverses this higher Gauss sum. But as I say, these sums fully classify the form. So if so time reversal takes these Gauss sums and inverses them mod 8. If they are, or if it's infinity, then it goes to infinity as well. And we just look at the fixed points of this action, 0, 4, and infinity. and this corresponds to real Gauss sums. So they are either real numbers or 0, which is also a real number. And this allows us to classify all. This provides us with the full classification of time reversal symmetric bilinear forms on finite abelian groups. We can do odd case by hand, and we can do the even case with these higher Gauss sums. And so far I was talking only about bilinear forms, and then I'm trying to find a quadratic refinements that are also time reversal symmetric, and the correspondence is not 1-to-1, but you can see the analysis in our paper. But after all, it packs in a very neat result. So we have this finite group, we have a bilinear form, quadratic refinement, and this is a T-symmetric if and only if all the higher Gauss sums are real numbers. So which means, yeah, these are including 0. So for all n integers, but not all of them are independent. So it is actually a finite number of conditions. So we don't need n. So we don't need n higher than order of d, but we don't even need even that much. So it's a very tractable description. So this is again for spin case, because I'm talking about quadratic refinements, but it's even simpler if I work with quadratic forms and with bosonic case. Then the condition is literally the same. So all I need to do is just to take all higher Gauss sums. Right. And so now, yes, this result, the announced result. So pointed MTCs, again, systems of abelian anyons with their F and R symbols, with their topological spins, they are fully fixed by a quadratic form on a finite abelian group and up to gauge equivalence. And we can prove that this MTC is time reversal symmetric is if and only if the corresponding quadratic form is time reversal symmetric, as expected. And here by time reversal symmetry, I mean that so it's a unitary category. So I complex conjugate, or I mean, I Hermitian conjugate all the F and R symbols, and everything checks out. I mean, I'll have a braided monoidal equivalence that, well, after all, connects this category and its reversal. Yeah, and this is the structure for super MTCs. Again, there is no quadratic forms inside, and I hope I hope it's satisfying to see, because I realize that this quadratic refinement is a bit confusing, but again, so the question was to classify abelian Chern-Simons, not MTCs. So, and in order to answer that for Chern-Simons, we needed quadratic refinements, but as a equivalently, we obtain a classification of time reversal symmetric pointed super MTCs, and this is how it looks like. So I can have any time reversal symmetric abelian anyons here. I have some number of semions. So they are not included in time reversal symmetric theories in the bosonic case. They can never be time reversal symmetric in the bosonic case. So this is why it's extra, extra data in the that appears on the spin case. So I have some number of semions, and I have a fermion, this S vector, right? But this is what we know. We know everything about this. So we just have a quadratic form. We form all these higher Gauss sums. So we don't even need to, we don't need anything. We just take all the we take all higher Gauss sums and check if they are real.
Excuse me.
Yes.
Sorry, what's the formula in the top? This little n inside this exponent 2 pi I n q hat. What's this?
Yeah. This is just the label of the higher Gauss sum. So n equals to 1 gives me the usual Gauss sum, right? And but I need all of them.
I see.
Well, yeah, I mean,
So
as I said, in this quadratic form business, they are very much dependent.
And then the first one that require n equal to 1 will imply the summation Gauss sum will be this exponent of 2 pi I central charge over 8.
Oh, so they all in the for abelian ions, they're all roots of unity, 8 roots of unity, or a 0. So yeah, so we have a theorems that n equals 1. This is the usual Gauss sum for the MTC, and it's never 0, and it's well, in the abelian case, it's a root of 8th root of unity, right? Well, sigma, or we can also call it central charge over 8. Yeah, and it's never 0, but higher ones can be 0, and we still need these numbers. So I don't know if you're familiar, but this is a very these higher Gauss sum also appear when we study Wood groups of well, topological order, MTC, and here we consider n's that are coprime to the order of d, or more precise, it must be it must be coprime to the order of the T matrix, right? And these Witt groups, these Gauss sums never vanish. Well, yeah, it depends if it's makes it clear for you, or more clear or less clear. I mean,
Is that somehow also related to this people call higher Carol?
No, it's exactly the same. It's exactly the same. Okay, so people usually say higher central charge, and they mean so. Okay, so this is the higher Gauss sum, right? And if it's not 0, in the abelian case, if it's not 0, then it's it's a 8th root of unity. And this is this Xi, what people call a higher central charge. And yes, it's literally the same. It's just it's just multiplicative, and because for me this, I consider Gauss sum with all m's, and they might vanish. So I cannot always define this higher central charge.
So can I rephrase your statement by the Bolzani? This is Bolzani theory here so far?
Yeah. So in this case, it's well,
the first
sorry.
line. First part of
So
can
yeah,
I
let me just add a page and say we have a bosonic theory, right?
So can I say the Bolzani theory will be T symmetric if the central charge and higher n central charge will OBC equal to 0 or 4 ma 8? Is that
not quite. So as I said, we can always define the higher Gauss sum. Yeah, I mean, sorry, I mean, I just repeat myself, but yeah, I want to make it clear. So what people do is they define the higher Gauss sum, which is all defined for all n, right? But if n is coprime to the order of the T matrix, right? Then Tn is its phase is the eighth root of unity, and the number of this root is then Cn is the higher central charge.
and the order of T is just a rank of the number of anion type for abelian theory? Also
They're certainly related.
T
Yeah,
is
this is the accurate statement, but
so T is just a T
yeah. To the yeah. Let me see. Stick to the abelian anions. So yeah. So just the order of the group, right?
When you write order of T, you mean the modular T matrix?
Yeah.
Then that's the same as the number of anion types, the rank.
Yes.
And then you require this higher Carlson charge.
So no. So let's see. So I'm saying that this is the higher central charge is defined in in not for all n. So for example, if I take some simple, if I take a one semyon, for example, its second so if I take right, if I take a semyon theory, so q of x is x squared over 4, right? So I have so the first the first Gauss sum is 1 plus I over so it's e to the 2 pi I 1 over 8, and so this is the second Gauss sum, the usual Gauss sum of a semyon, of a single semyon. But the second Gauss sum over square root of 2 is just 1 plus minus 1 over square root of 2, which is 0. So it does not define you a higher second central charge, but for me it is important. I mean, this number for me is important. In fact, just looking at these two sums, T1 and T2, I can tell you which theory we're talking about, and I can tell you if it's time reversal symmetric. Well, it's not, because this is not time reversal symmetric. So when people talk about higher central charge, they would discard this Gauss sum.
Okay, no problem. Yeah,
Yeah.
there's some, but probably I can ask afterward. But there's also some relation between this higher central charge and whether the boundary is gappable.
Yes, exactly. So if all the higher central charges are 1, then it's gappable. Higher central charges, again, in this definition, it's not all Gauss sums. So this is what I'm requiring. Knowing all Gauss sums is much more than knowing all even all higher central charges. And moreover, I'm I'm requiring that the higher all higher Gauss sums are real, while this gapable condition requires that some of the some of these Gauss sums have zero phase, have trivial complex phase. Okay. Yeah. So is it clear? Well, again,
You can continue.
yeah. Well, yeah, just briefly, I want to, mention our conjecture about T-symmetric, general T-symmetric MTCs. So things here are much more complicated. We have a lot of data that is not packed into, just a quadratic form. And it's not even obvious, that, for example, if you can, invert S, well, if you can conjugate S and T matrices, will it, be sufficient that F and R symbols are conjugated, right? Because S is a trace, so well, it's not obvious at all. So, but on the other hand, as I mentioned, these higher Gauss sums, so they are not longer eighth root of unity. So they are, and this is a very, very strong condition on lots of, it's a lot of algebraic conditions. And definitely it's necessary for them to be real in order to MTC to be time reversal symmetric, but it's not clear if it's sufficient. So our conjecture that this is a sufficient condition. So first, we checked it on one example. So there is a PSUN level n. And here is the list of Gauss sums. So 1, 2, 3, 4, 5, 6, 7. This labels the number of the Gauss sum. They all minus 1 plus 1. And n labels the, this n Rankin level of PSUN. So there is, this time reversal symmetry here is the, it is like was known long ago because it's a like sort of level rank duality. Yeah, and these are the phases of the Gauss sum. It doesn't even vanish.
But it's generalized to not an Abelian, is beyond non-Abelian Chern-Simons, is it?
Yeah, I mean, well, our results do not generalize. We just conjecture that it will generalize. This is how we define the any higher Gauss sum. So dx is the quantum dimension of a reducible object, and theta x is the topological speed. Well, I mean, or the tx eigenvalue. Sorry, well, the eigenvalue of T matrix. Yeah, I'm just saying that it is a conjecture, and we checked it, and we also there is a formula for the Reshetikhin-Turaev invariance. So if we have a length space ln1, and there is a relation between Reshetikhin-Turaev invariance on the length space and its orientation reversal, and this relation goes as the relation of the Gauss sums, assuming they are not zero. Then there is this relation, and if you want these partition functions to be the same, then the Gauss sums must coincide Tn and T minus n, there must be a relation between them. And also, well, there is one more argument that, we kind of expect that we can define a modular tensor category over the field of reals, which is not easy, but yeah, we assume we did that, and certainly the Gauss sums, and yeah, and we say that we work over complex numbers, but our time reversal symmetric theories, they are secretly coming from real MTCs tensored with the usual vec c. So vec c has a trivial Gauss sum, the identity, and this must have a real Gauss sum. So this might be a mechanism behind the time reversal symmetric MTCs. They are secretly real. And if it's the case, then of course this conjecture should follow. Yeah. So right. If I wasn't that much over time, I would tell just one more comment on the on lattices whose quantization is time reversal symmetric. We can actually describe them all together, but we don't know when they are classically time reversal invariant. We just know when quantization of a classical lattice will lead to time reversal symmetric anyons. Yeah, I can do that if you want.
Yeah, since we are here, you can just say whatever you want.
Thanks. Yeah.
Sorry.
Yeah. Thank you, Max, very much for your questions, and yeah.
Feel free to continue.
Yeah, or maybe you have questions.
Not right now. Just I think
yeah.
you make a summary of what you want to say. I think it's very good. It's all.
Yeah. All right. So the summary. Yeah. Well, again, so we had a. Yeah. So we wanted to discuss this concrete problem, and there are 3 levels to this. There is a classical Abelian case, right? Integral lattices, there is a quantum Abelian case, and there is a general quantum case. And well, the quantum data for non-Abelian Chern-Simons is almost any MTC, except Hagerup. And we can say something about integral lattices, and we can say we know everything about the Abelian group. So this is why it's green. And we can say a little about general modular tensor categories. And yeah, and the main result is, of course, the complete classification of quantum Abelian time reversal symmetric Chern-Simons and pointed MTCs.
But the last case is only consider the bosonic case, right? And the first 2 you can include the fermion.
Well, I mean, if it holds in the bosonic case, well, I guess there will be no issue to define over the. I think it's just 2 different levels, of complexity. So even though super MTCs, general super MTCs, they do not split. So if you have super MTCC, it's not necessarily, if it's like super, okay, I'm just trying to say that super MTC is not necessarily a product of an MTC and a fermion. So this fermion can be, need not be split. This adds difficulty, of course, and yeah. So we have like a couple of arguments why would it hold, but yeah, again.
I remember maybe the Fermionic case, probably time reversal requires statement more like a central charge mod 1 is 0 or 1/2, something like that. Instead of the case we kind of just discussed earlier, the bosonic is like central charge 0 or 4 mod 8, right?
So right, but I think it's the same statement. I'm just if it depends on what you call central charge. Here, I mean, okay, here I have
I see.
well, so central charge in the Abelian case, well, central charge mod 8 is the sigma mod 8. Am I even right? Wait a sec. So no, wait a sec. So in the bosonic, well, in the Abelian case, so central charge is always rational. I'm just trying to say that it's probably the same statement.
Okay.
Right. So you're just saying that the Gauss sum is a real non-zero real number. Yeah, and I'm saying the same. So it's true for it's already correct for the bosonic case. So it's not a fermionic feature. I have a bosonic.
Sure.
Oh, do I even have them? Okay, I'm not sure. Yeah. Yeah, so the last thing I wanted to comment on is, since you allow me to go on.
Actually, I was saying something wrong. I think it's more like for Fermionic case, it's like a 0 or 1/4 mod 1/2. Something like that. But anyway, we can discuss afterward. It's a 0 or mod 1/2 because it's like you can stake fermionic invertible theory, which differs central charge by 1/2.
I see now. Yeah. Okay. Then yeah. All right. So the last thing I wanted to say is this. There are some results by Nikulin about integral lattices that we can apply here. I believe it's 1980. So assume our integral lattice can be embedded into a unimodular lattice. So M is unimodular. It means that the discriminant group is 1, no anyons. So we kind of embed in our classical K matrix into a unimodular lattice. And we assume that, so there is this embedding phi, and we assume that M modular, so lambda is explicitly realized as a sublattice of M. And assume that M modular lambda is also a lattice. It's a non-trivial condition. So for example, 2z is embedded into z, and their quotient is z mod 2, and it's not a lattice, right? It's not free. So we require that M should be embedded, lambda should be embedded into some unimodal lattice that is, and such that the quotient is also a lattice. And then we can find the orthogonal complement. So M is unimodular. It's equipped with some form. I don't know. Let me call it N. And using this form N, we can define the orthogonal complement to lambda. And if it happens that the orthogonal complement to lambda is lambda, then the quantum data, the symmetric form, will be time reversal symmetric. The symmetric form coming from lambda. Sorry. Okay. So we start with some K matrix K, and when with the Chern-Simons functional using this K matrix, and assume we have a bigger Chern-Simons with larger rank that is trivial as annual theory, like it's in the quantum level. And if there is if we can fit within this larger theory another copy of our classical theory, then this is time reversal symmetric.
Classical physics is a group of physics theories that
Thank you, Siri.
more complete or more widely applicable theories. Do you want me to keep reading?
No. So yeah, this is the last thing I wanted to comment on. That's that might be useful. Yeah, so for example, the A4, the Cartan matrix of A4 is embedded into E8 self-orthogonally, like we needed, and it is time reversal symmetry, same as D4. Yeah, all right. So
you're writing in terms of Cartan matrix here.
yeah. So A4 and D4 and E4 are Cartan matrices. I use them as K matrices.
Okay. So
Yeah.
EA is rank 8, E4 is also rank 8, or
E8 is rank 8, and A4 and D4 are rank 4. So
okay.
the thing is that the complement of A4 within E8 is A4, another copy of E4.
And you are embed in terms of the lattice inside.
Yeah, it's like
as a sublattice.
Yeah, it's as a sublattice, right? So I have like a lattice M, and I have like two, say, an example, like if I had a two-dimensional lattice M, and I could embed two lattices, lambda, and it's orthogonal.
And the statement about A4, D4 here is that what's the significant about them to embed into the
E8? Say again, please. The last sentence.
What's the significant? What do you mention this fact?
Oh, well, because this give us time reversal symmetric theories, like quantum time reversal symmetric. Okay.
I see. You mean for A4 and D4 you can have?
Yeah. No, I mean if I take K4, if I take K matrix being A4 or D4, and then I calculate the discriminant group and all this business, there will be time reversal symmetric. For D4, I had this. I had them in my paper, and for D4, I believe this is gonna be. Okay, I don't want to. I don't quite remember, but it seems to me that for D4 I have this x squared plus xy plus y squared over something like over 4. I feel like this is what I'm getting for from D4, the quadratic form of x. I need to double check.
And then for E8, can you have a time reversal symmetric?
Oh, well, E8, at the quantum level, E8 is kind of trivial. So, well, technically it is time reversal symmetric.
But it's chiral.
Mm,
It's chiral, but you count it as time reversal symmetric.
right. So,
So it's chiral central charge 8, but
right. Uh, so okay. Well, right. So that's why I consider sigma only modulo 24, and in this case it's fine. It's like if I consider sigma mod 24, then I can have perfectly fine T-symmetric stuff. But in the anyons, well, yeah, it depends on what you want to include. Well, I mean, what I can do always here is add minus E8, right? So
so maybe I can rephrase. Say you are consider time reversal symmetric up to staking ES state. You will not consider central charge.
yeah,
Yes.
I mean, for me, sigma mod 24 is fine, and if sigma is 12, then it's time reversal. It can be time reversal symmetric, for example. But yeah, as I mentioned, it's not. I don't think it's an issue, because if you allow me to add like trivial anyon, like no, like K matrices without anyons, then I can always get rid of the central charge. But okay, standing alone, E8 should not be time reversal symmetric. I tend to agree with that. Yeah.
And EA is also signature is 8, right?
Right.
Yeah.
Yes, it is. Yeah, in the real material, yeah, E8 should be different phase, and yes, it has it is chiral. I agree.
I think
Yeah,
there's
but
a lot of information, but it's very nice.
oh yeah, thank you. Well,
I'll understand better later, but I think
yeah, I don't know. I feel like I should maybe announce you the result first, so you didn't need to worry about the quadratic refinements. Maybe.
okay.
But yeah, thank you very much for having me here, and yeah,
Thank
maybe
you.
we can stop recording and
Thanks very much. If there are comments from the audience, you can still ask.